Hi dear students of +1, medical, non-medical and respected teachers. Today I am going to discuss elastic collision in two dimensions. So suppose we have a body of mass m1, body A, moving with velocity u1 along x-axis. Suppose we have another body B of mass m2 lying at the origin of x-axis and y-axis at rest. Body B is at rest, so that u2 is equal to 0. Now suppose body A collides with body B. It is not a head-on collision. Suppose after collision, body A goes in this direction, body B goes in this direction. That's why it is a two-dimensional collision. Suppose theta 1 is the angle which direction of motion of body A makes with x-axis. Theta 2 is the angle which direction of motion of the body B makes with x-axis. Let v1 and v2 be the velocities of the bodies after collision. So that m1 v1 is equal to momentum of the body, m2 v2 the momentum of the body B. So m1 v1 and m2 v2 are the momenta of body A and B respectively. Then this momentum m1 v1 can be resolved into two rectangular components, m1 v1 cos theta 1 log x-axis, m1 v1 sin theta 1 log y-axis. Similarly, momentum m2 v2 can be resolved into two rectangular components, m2 v2 cos theta 2 along x-axis and m2 v2 sin theta 2 along y-axis. So since the collision is elastic, so both law of conservation of linear momentum and kinetic energy are applicable. Even the collision is elastic, but it is oblique. It is not head-on collision. It is not one-dimensional. It is two-dimensional. So we have to apply conservation of linear momentum first about x-axis and y-axis separately. So by law of conservation of linear momentum along x-axis first. What is the momentum of body A along x-axis? m1 u1 before collision. Momentum of body B along x-axis before collision 0. So total momentum before collision is m1 u1. And after collision m1 v1 cos theta 1 plus m2 v2 cos theta 2. So these two components are added which are acting along x-axis. So m1 v1 cos theta 1 is the momentum component of momentum of body A along x-axis. m2 v2 cos theta 2 is the component of body B along x-axis. So we have m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. Suppose this is number 1. Along y-axis. Now there is no motion along y-axis initially before collision. So total momentum before collision is equal to 0 along y-axis. So is equal to, now after collision it is m1 v1 sin theta 1 along positive y direction. It means minus m2 v2 sin theta 2 along negative y direction. So these two components are opposite, so they are subtracted. So net linear momentum after collision is m1 v1 sin theta 1 minus m2 v2 sin theta 2 is equal to 0. So this is number 2. Then we law of conservation of kinetic energy. Half m1 u1 square, kinetic energy of body A, plus 0 because it was at rest is equal to half m1 v1 square plus half m2 v2 square, because kinetic energy is scalar quantity. So v1 is the velocity of body A, v2 is the velocity of body B after collision. Now we have three equations 1, 2, 3. But we have four unknown quantities v1, v2 and theta 1 and theta 2. So to find v1, v2, so we have to find theta 1 and theta 2 practically. So when theta 1 and theta 2 is equal to 0 degree, or theta 1 is equal to theta 2 is equal to 9 degree, or theta 1 is equal to theta 2 is equal to 3rd degree or 6th degree, any angles may be given. So we have to find v1 and v2. So I will discuss one case when theta 1 is equal to theta 2 is equal to 0 degree. Then cos 0 is equal to 1, So from equation number 1, so we have m1 u1 is equal to m1 v1 plus m2 v2, say equation number 1, or it can be written as m1 u1 minus v1 is equal to m2 v2. Similarly, from second equation becomes 0. Third equation, half m1 u1 square is equal to half m1 v1 square plus half m2 v2 square. Half of cancel throughout, or it can be m1 common u1 square minus v1 square is equal to m2 v2 square, or u1 square minus v1 square can be written as m1 u1 minus v1 u1 plus v1 is equal to m2 v2 square, dividing 2 by 1. So m1 u1 minus v1 cancels, so we have u1 plus v1 only left hand side, m2 cancels, we have v2. So u1 plus v1 is equal to v2, or u1 is equal to v2 minus v1. Again, relative velocity of separation is equal to relative velocity of approach when theta 1 is equal to theta 2 is equal to 0 degree. That is, it becomes a one-dimensional collision special case. So u1 is velocity, u2 0. During collision, after collision they will get separate. So how to find v1 and v2? To find v1 and v2, from this equation, substitute the value of v2 in equation number 1 as usual. So m1 u1 is equal to m1 v1 plus m2 into v2 means u1 plus v1. Simplifying, m1 u1 minus m2 u1 is equal to m1 plus m2 into v1, or v1 comes out to be m1 minus m2 into u1 upon m1 plus m2, so which is required expression for velocity v1, first body after collision. Similarly, taking v1 is equal to v2 minus u1, so we can find v2 is equal to 2 m1 u1 upon m1 plus m2. So from 4 and 5, we see that we have calculated velocities v1, v2 after collision when theta 1 is equal to theta 2 is equal to 0 degree. Similarly, when theta 1 is equal to theta 2 is 90 degree, then this equation has no role. So take this equation, m1 v1 minus m2 v2 is equal to 0, or this equation again proceed the same steps, find the value of v2, substitute in equation number 1, and so on. So we can find the values of v1, v2 as usual. Similarly, when any angle is given, so here any angle may be given, theta 1 is equal to theta 2 3rd degree, maybe 6th degree may be given. So then we can find velocities of body after collision. So this is elastic collision in one dimension as well as in two dimension. So one dimension is a special case. So this is elastic collision in two dimension. When body move in different directions in a plane after collision, such a collision is said to be elastic collision. Both momentum and kinetic energy remain conserved. This is all about elastic collision in two dimension. In next video, I will discuss inelastic collisions in two dimension and one dimension. Thank you. Till then, all the best. Be happy. Good luck.